population. And also we have prediction that in 2050 our population will be 9.8 billion, and we need to produce 70% more food than today. So it is a big challenge for us, especially for the plant biologists. And on the other hand, we know that global warming and climate change, they are disrupting our food production in a multifarious way, directly or indirectly. Many kinds of biotic stresses, abiotic stresses, they are reducing our productivity significantly. Among the abiotic stresses, for example, salinity, drought, extreme temperature, flooding, toxic metals and metalloids, atmospheric pollutants, they are reducing our crop yield, and it is estimated that the yield reduction may be up to 65% due to abiotic stress. So finding the ways to tolerate, to adapt abiotic stresses by plants are the urgent tasks for biologists, because it is not the strongest of the species that survive, not the most intelligent, but the one most responsive to change. So this is very important, how we can make our plants adaptive to the changing environment. So I think one of the most innovative and promising solutions to address these important challenges consists of the use of biostimulants, because they have many aspects we can harness. So biostimulants has no specific legal definition, but in a broad scale we can say that substances and all microorganisms whose function might apply to plants or the rhizosphere is to stimulate natural process to benefit nutrient uptake, nutrient use efficiency, tolerance to abiotic stress, crop yield and quality, independently or due to the existence of nutrient content in those stimulants. So this is the definition by the biostimulants industry council. But there are many biostimulants in the world nowadays. We can classify them as acids, some of the organic acids, some of the microbials like fungi, some beneficial bacteria, microbial symbioses, and many plant extracts like seaweed extracts, many other plant extracts, algal extracts, and some others like inorganic salts, some enzyme extracts, proteins, agroindustrial byproducts. These are considered as biostimulants, and there are many more. So there are many stimulative effects by these biostimulants. For example, nutrient and water uptake or their availability, increase plant growth because they secrete many stimulative molecules. They can help them to enhance their growth and development. They have many signaling molecules or many other beneficial molecules. They can make them adaptive or tolerance to biotic stresses like salinity, extreme temperature, drought, flood, etc. They improve the yield and quality of the crops. They improve soil health also. Some of the biostimulants we can apply, and they can change the status of soil, specifically some of the microbes, and increase resistance to biotic stress as well. But today our talk is about abiotic stress, and we found that there are many networks of biostimulants with plant and soil, especially for enhancing the nutrient use efficiency, which is very important in terms of soils and soil-plant relationship. So we can harness the potential role of biostimulants in improving plant-soil interaction or plant-microbe interactions or plant-environment interactions. So this is very important for our future food production. If we can see the scope of database, we can find that in the last 20 years, the number of publications are increasing drastically on the subject of plant biostimulants. You can see that every year scientists are doing research and they are publishing on plant biostimulants. So this is a promising area of research. For example, seaweed, they have multiple roles in improving plant abiotic stress tolerance. For example, Hasanuzzaman is a very promising seaweed, and their extracts have many compounds. Those are helpful for plant growth enhancement or plant stress tolerance, like alginic acid, mannitol, many minerals, amino acids. These are very beneficial to confer plant abiotic stress tolerance. For example, in our preliminary study, we found that under drought conditions, seaweed extracts and alginic acid, they confer tolerance to drought stress, similar to drought, like 50% field capacity and 25% field capacity. We found that in both of the cases, seaweed extract and alginic acid, because alginic acid is a component of seaweed extract, so they could mimic the activities, and they showed that the addition of seaweed extracts and alginic acid could protect the plants from drought stress, because they could provide osmoprotectant, because they have some molecules, they act as osmoprotectant, or they enhance the defense defense mechanism by which they can protect the plants from, for example, this is the experiment with soybean, and we found that electrolyte leakage and leaf-related water content. In case of electrolyte leakage, they reduce the leakage levels. The membrane was stable, and they protected the water loss, and that's why the electrolyte water content was improved due to the application of some extract. And many of the biostimulants, they have the capacity to improve the antioxidant defense system. That's why they could survive better under stressful conditions, especially oxidative stress condition. And because you know that under stressful conditions, plant excessively generate many of the radicals or non-radicals. They are termed as antioxidant species, which are the reasons for oxidative stress. But plant should have very well-developed antioxidant defense system consists of agenetic and non-agenetic component. But we found that in our study that some extract could mitigate many allergic stresses like arsenic toxicity by modulating antioxidant species metabolism and reducing oxidative stress. Biggest surprise, and our results showed that superoxide radicals generation both under arsenic and cadmium was significantly lower when we treated the plants with seaweed extracts. So this is our unpublished result, and this result we published in safety, and found that plant high, fresh weight, dry weight, healthy water content. These are improved when we supplemented the plants with some extracts. Electrolyte leakage was lower. Proline content was also regulated by seaweed extracts. And finally, the hydrogen peroxide content and malolactate content was significantly lower due to the application of seaweed extracts. That means that could improve the antioxidant defense system. That's why the generation of antioxidants was lower. And this is the simple mechanism that under arsenic stress, many parameters, including plant antioxidant defense system, was looked at. But finally, spray the plants with seaweed extract, they could reduce the antioxidant species generation and improve the daily water content, as well as the entire defense system, especially antioxidant defense system, was upregulated due to the application of seaweed extract. So this is one of the mechanisms. So also we tried utilization of nanopotash and seaweed extract to check the rice plant, and we found that under moderate and severe salt stress condition, seaweed extract and nanopotassium, and also their interactions or their synergistic effect showed that under both cases, antioxidant species generation was lower when we supplemented plant with these biostimulants. And because they could improve chlorophyll content, fluorescence, they improve the biomass production and enhance the non-enzymatic and enzymatic components of the antioxidant defense system, as well as they lower the generation of antioxidant species and improve the relative water content. Also another component, glycolic system, was also improved due to the application of nanopotash extract. And you can see the phenotypic picture that both root and row was tremendously improved due to the application of seaweed extract alone or in combination with nanopotash. So this is a promising area of research, how they counteract salt stress in case of rice. Moringa leaf extract is another promising biostimulant which can be applied under stressful conditions. We found that under arsenic stress, moringa leaf extract would revive the stressful environment in rice plant. Also, seaweed extract as well as moringa leaf both plant extract we tested in rice plant, and we found that they could minimize the cadmium oxidative stress in case of rice. Especially, we can indicate the role of glutathione, because both plant extract they improve the glutathione redox system. Also, the content of reduced glutathione, which is very important in case of heavy metal stress, because they have a direct role in phytogenetic synthesis. This is very important to transfer the xenobiotics or metals to vacuum. So this is very important. Also, glutathione act as a signaling molecule. So as a result, we found that both ascorbic acid pool, that means ascorbate pool and glutathione pool, were significantly improved when we supplemented the plant with moringa leaf extract or seaweed extract. So this is very important how we can apply this kind of extract for the improvement of our plant redox system. And we found that finally that when medical the number of field unfilled grain, 1,000 yield. Many yield parameters, they were also significantly improved due to the application of moringa and CP experiment. And also same main reason was antioxidant defense system. Also they are associated with other things like increased water uptake, enhanced photosynthetic and assimilation, accelerate production, stimulation of antioxidant defense as I told earlier, and also improved glycolysis system. This is also an important protective system that can indicate the level of methylglycol in plants, which is also a cytotoxic compound. We found that some organic acids, so we tested humic acid with biochar, and we found that combined humic acid and biochar, they improve the physiological and biochemical process of rice under arsenic stress condition. And almost the same mechanism we found that under arsenic condition, both biochar and humic acid, we tested 2 doses of humic acid and 2 doses of biochar. They significantly reduce the superoxide radical generation and hydrogen peroxide generation in plants because they could enhance the antioxidant defense system. Then we also interested in use of microbes for plant stress management. In the last decade, there are plenty of works also have been carried out by many researchers on the beneficial roles of microbes, because we call them bioproductory, because they are very valuable in terms of soil improvement, plant stress tolerance, and many other protective roles. They can improve yield and quality, they can stimulate plant metabolism, they can optimize the nutrient uptake and assimilation, also their efficiency. They can protect the plants from not only from abiotic stress but also from biotic stress and enhance the soil microbial activity. So altogether, their application is very beneficial in plants under normal condition and of course under stressful conditions. So now we tested some beneficial microbes and found that they also modulated reactive oxygen species and iron homeostasis in combined salt and cadmium stress, and we found that these microbes are very effective. Also we tested them in especially Bacillus subtilis, this is one of the beneficial bacteria. And we found that in case of soil plant, Bacillus subtilis would convert the salt stress tolerance by coordinating osmoregulation, ion homeostasis, antioxidant defense, and methylglycol methylation system. And we can find that at any level of salt stress, this bacteria would elevate the oxidative stress by limiting the generation of both hydrogen peroxide and superoxide radicals. And the main thing is that they could enhance the activities of some of the vital antioxidant defense system enzymes like superoxide dismutase, catalase, peroxidase, glutathione S transferase, and glutathione peroxidase. So these all together could minimize generation of hydrogen peroxide, and also they could detoxify the xenobiotics. So this is very important. So protective system, and in our case we found that Bacillus subtilis could upregulate this system very well. As a result, we found tolerant plant. Also, they could decrease the sodium-potassium ratio. As you know, that potassium is very vital for conferring the plant's tolerance to abiotic stress. And also, they improve the calcium content in plant. Calcium is also another signaling molecule. So, in our study, we found that this iron homeostasis was very nice under salt stress when we supplemented them with Bacillus subtilis. And also, we isolated some endophytic organism rhizobacteria, especially such as Paranochondria, Delphia. So we applied this bacteria and found that both under cadmium score, moderate or severe cadmium stress, these bacteria could confer tolerance by modulating antioxidant defense and glycolysis system. Especially GPX and catalase activity was significantly improved when we applied this bacteria, endophytic bacteria. And as a result, the yield components and yield of brassica campestris was significantly higher when we applied these two bacterial isolates. So this can be another promising area of research, and we can apply them as biofertilizer under stressful conditions. In our case, we tested cadmium, but in many other stress also it can be applied. For salt stress, also plant growth promoting rhizobacteria can be an alternative approach to convert them stress tolerant, especially salt tolerant, because they have multiple reasons like phosphorylation, siderophore production, maintenance of water and nutrient balance, increased sodium potassium ratio. They could actually minimize the sodium potassium ratio, modulation of plant antioxidant defense and osmotic protection. There are many beneficial effects, and we found that we isolated some bacteria. One is Bacillus subtilis, another one is Bacillus ariavarti. Both bacteria enhance plant growth and also regulate the antioxidant defense and iron homeostasis under sodium chloride stress, salt stress, and many parameters. We tested them in rice plant. We applied them at 35 days after transplanting, and we found that sodium content was significantly lower when we applied Bacillus subtilis or Bacillus ariavarti. But potassium content was increased. As a result, sodium-potassium ratio was reduced when we applied Bacillus species. Specifically, ascorbate redox pool was significantly higher when we applied this bacteria. As you know, the AS/TH ratio was significantly higher. Also, some antioxidant enzymes like protein peroxidase, protein S-transferase, and lipoxygenase activities were significantly regulated or improved due to the application of Bacillus subtilis and Bacillus ariavarti. Also, catalase, peroxidase, and superoxidase nuclease activities were significantly higher when we applied Bacillus subtilis and Bacillus ariavarti. And also, photosynthesis is one of the important parameters, and some relevant parameters like swab value, total conductance, and chlorophyll fluorescence was significantly improved when we applied this, because they could enhance the nutrient use efficiency that help the plant to enhance the photosynthetic capacity. And most importantly, indole acetic acid content, which is one of the most responsible for enhancing plant growth, was significantly higher when we applied Bacillus subtilis and Bacillus ariavarti, and we found that this compound was significantly upregulated due to the application of bacteria. So it helped the plant. Also, we tested some of our isolates. In case of arsenic stress, we found that compared to uninculated plant, RAP2, GP1, GP3, these bacteria could elevate the arsenic stress, and the plant are very much healthier than the uninculated plant in case of arsenic stress. This meant another opportunity to use these bacteria for metal tolerance. Also, we found that compared to uninculated plant, hydrogen peroxide and also superoxide radical generation was significantly lower. So we can do further research with these isolates of bacteria. So this is the simple mechanism. You know that as like previous, chlorophyll content and photosynthetic parameters, also indole acetic content was significantly higher. They lowered the reactive oxidant species generation. They improved the redox pool of ascorbate and glutathione. They enhanced the activities of ascorbate peroxidase, monodehydroascorbate reductase, and some vital antioxidant defense enzyme, also the oxidase enzyme. So altogether, they provided beneficial role in improving plant arsenic tolerance. So this is a promising area of research, as I mentioned earlier, and this is 2 or 3 years old data, but still we can see that the cumulative annual growth rate of biostimulant market is increasing year after year, and this is still it is 12.5% or higher. So there is a great demand of biostimulant in global market also. So we need to find out appropriate biostimulants that can really enhance plant growth, yield, also their quality, both under normal condition and of course under stressful condition. But there are some challenges, that scientific challenges we have. Still we have lack of research and development. We need to fine-tune the biostimulant which is the most potential and sustainable. So we have to find out the appropriate biostimulant. Some technical challenges like proper guidelines and supports. This is very important. And of course, some regulatory challenges, because we are working with microbes, some extracts, some other things. So there are some laws, some policies. So this is also another challenge for promoting this biostimulant for actual life. So we are talking about sustainable development goal, and we want to double the crop production, but still we are so far. So we have to understand the plant defense mechanism. We have to make the plant adaptive to the stressful condition under the adverse environment, how plant can survive. So we have to work with many effective approaches that can improve crop yield and quality in a sustainable way. So we already know that there are many critical roles for biostimulants in the agriculture of the future, but critical scientific steps required for an optimal selection and characterization of biostimulant compound because there are diverse biostimulants, many kinds of biostimulants. We have to analyze them, we have to continue our research to develop optimum solution for specific economical needs. So we have many problems, but science is the answer. So we have to harness the power of science. So biostimulants for crop production and sustainable environment is very promising, and we have to continue our research on biostimulants for our agriculture. So I want to thank our founders, donors, and also our collaborators, and finally the organizers for inviting me as a keynote speaker of this very prestigious conference. Thank you very much.